Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the conference. Network Design. Oil and Gas Exploration and Production. This conference focuses on the design, formulation, and use of optimization models for the design of oil and gas production networks. Considering the dynamics of this production process, the formulated models can be used in the permanent redesign of the active O&G production network. Framework for optimize the network design of oil and gas exploration and production. The models presented are oriented to long-term analysis, of the order of years, and can be classified as reservoir recovery optimization. The oil industry includes global processes of exploration, extraction, refining, transportation and marketing of petroleum products. The largest volume products in the industry are fuels, natural gas, fuel oil, and gasoline. However, petroleum is the raw material for many chemicals, including pharmaceuticals, solvents, fertilizers, pesticides and plastics. The models are concentrating on the upstream of the supply chain of petroleum products. The image presents an example of the production and exploration infrastructure that can be included in an optimization model. In the case of offshore production, modeling can differentiate multiple types of platforms, such as fixed platform, TLP spar semi-submersible, and FPSO. The conceptualization of the field can be done based on the following principles. Well, it corresponds to the basic unit of production, reservoir. It corresponds to a set of wells that operate an oil deposit that is interconnected in the subsoil, and field. It corresponds to a set of multiple oil deposits which contribute their production to a collection and processing infrastructure. The collection infrastructure is composed of separator, production unit in which oil, gas and water are separated, collector. It is composed of a network of pipes that connect the fields with the separator, and tanks, storages of oil, gas and water, already processed. The topologies of the network can be very varied, since an O&G production facility can have multiple components of each type. Modeling the optimal design and planning of well fields. The Decision Support System, DSS, for design and planning of well fields will be called DPOF. DPOF must be made up of multiple models that interact with each other. Models may be solved in two ways. Coordinated, independent models that share results with each other, according to a logical data flow. Integrated, the models are integrated into a single mathematical model that is solved as a single mathematical problem. The best way is integrated, considering that it can solve the holistic optimization model until it reaches the optimal solution. The first model will be called LogFin. It is oriented to define the investments to be made in infrastructure necessary for production. It corresponds to a dynamic model that defines, for each period of the planning horizon, the investments to be made, and the network for short-term operation. As input parameters, it should consider the costs of investment, rate of return on capital, the costs of loans, payment period, and other financial considerations. Model constraints are related to investment logistics and financial risks. The main results of the model are NPV, net present value, of the investments, VAR, value at risk, cash flow, and network design for the first periods. The second model will be called SANDOP. It is aimed at simulating industrial operations for each possible network proposed by the investment model, LogFin. As input parameters, it should consider, at least, the forecast of demand of final products, raw material supply, operational costs, and sell prices. The model can be extended to consider other aspects such as technological innovation that affects the productivity of processes, new technologies, which may affect market prices, and others that are considered convenient. In general, all input parameters are uncertain, and it is appropriate to consider that this makes a stochastic programming model based on scenarios. This characteristic makes the LogFin model a coordinator of the evaluation of the scenarios to be considered in SANDOP. It corresponds to a dynamic model that defines, for each period of the planning horizon, the industrial operations, and the storages of materials. In certain cases, it may not be necessary to consider product storage, because it may have little impact on investment costs, and additionally, it may be considered that its offer is always provided by the market with stable prices. This is not the case for oil storage, where the market prices and the supply of oil and gas is uncertain with high volatility. The constraints of the model are related to the industrial production process. Normally, there are several alternatives to simulate this process. At one extreme we may formulate a very simple model, perhaps a few aggregate equations, that synthesize the process. At the other extreme, we may formulate a detailed model, that simulates the processes with great certainty. The decision is of the modeler. What is true, is that the available computer technology, computers plus solvers, allows very advanced models in this aspect. Therefore, the level of detail will grow exponentially in the next years. The main result of the model is the operational simulation for each period for each scenario. Data that are necessary to evaluate the future cost function, that generate the decisions of the present. The third model will be called ALM. Its objective is to simulate the assets and liabilities management, ALM, considering the results provided by LogFin and SandOp models. ALM is a modeling consolidated methodology that focuses on the financial modeling of companies. Its growth is generated at the end of the past century, in the financial sector, as a result of the Basel Accords. The minimum ALM modeling should be oriented to evaluate the NPV, for a pre-established ROI, return of investments. It will provide the financial statements, balance sheet of assets, liabilities and equity, income statement, profit and loss, after tax, royalties, and other contributions, and cash flow. Extended ALM modeling may include investments in alternative assets and liabilities, payment of dividends, capital repatriations, capital flow, and multiple currencies. In healthy logic, this model must be the coordinator of the holistic investment process, since it is the financial vice presidencies of the organizations responsible for endorsing investments in production assets. The results of the holistic optimization process are probability distribution functions, for the primal variables, and the dual variables of all DSS models. For example, the NPV. In simpler modeling, these distribution functions are obtained using spreadsheet simulation models. The results are not comparable, because of the methodological difference in the approach. The mathematical optimization models that may integrate a comprehensive decision support system, for a company dedicated to the exploration and production of ONG, are Oiled POF, well drilling infrastructure and network planning. Oil POP, optimization of the investment portfolio of investment, exploration and production. Oil NPO, design of oil exploitation networks, and Gas NPO, design of shale gas exploitation networks. Hereinafter the company will be referred to as Oil Express. Two papers have been taken as a reference to structure the proposed model. They are Multi-Stage Stochastic Programming Approach, for Offshore Oilfield Infrastructure Planning, Under Production Sharing Agreements, and Endogenous Uncertainties, and a Multi-Stage Stochastic Programming Approach for the Planning of Offshore Oil or Gas Field Infrastructure Under Decision-Dependent Uncertainty. Slides from the author of one of the authors of the papers, Dr. Ignacio Grossman, Director of the Center for Advanced Process Decision-Making at Carnegie Mellon University, have been used. The examples that will be presented are focused on the development of infrastructure to produce shale gas or to produce oil. The two problems are similar but is not equals. During the presentation we will refer as the shale gas model and the oil model. Topic: Optimal planning of shale gas well operations. The main characteristics of the shale gas problem are: the composition of the extracted gas varies considerably, even within development areas. These can be classified as producing wet or dry shale gas. Decline rates of 65 to 85% within the first year of production are not uncommon, and to ensure a steady supply of natural gas supply, producers must drill many new wells continuously. The image shows the expected infrastructure expansions of natural shale gas supply chain, in 2009. At that time, there were no mathematical models, specially oriented, to support the development of the shale gas value chain. The main decisions to be made are: site construction, where and when to construct a well site; development schedule, where, when and how many wells must be drilled; delivery node selection, processing plant or compressor; and gathering network, where to lay out pipelines. The shale gas development problem involves a large number of discrete planning and design decisions that need to be addressed simultaneously. The image presents a typical timeline for the development of shale gas-related projects. The process of infrastructure development involves 5 stages, which are: site construction, rig on site, drilling, completion, shut-in, and production. Other activities are related with freshwater acquisition, flow back of the freshwater, pipeline construction, and compressor installation. 2 models are required for the optimization of the shale gas decision-making process: optimal investment in drilling in shale gas supply chains, and optimal water management in shale gas production. This presentation concentrates on the first model. The qualitative model description of a shale gas design production process is: the mathematical problem. Maximize net present value revenues from natural gas sales, expenses for well development, pipelines, compressors, royalties, freshwater, rig transitions, and others. Subject to well site construction, shale gas production, shale gas flow balances, pipeline and compressor sizing, water management, rig allocation, and gas quality specifications. The fundamental modeling assumptions are: discretized planning horizon, commonly annual quarters; drilling activity constrained by seasonal freshwater availability, seasonal weather conditions, development permits, CapEx and others. Long-term production forecasts for all potential wells are given. Gas composition at every potential pad is given. Freshwater demand for hydraulic fracturing is a fixed volume for every well. Pipeline pressures within the gathering network are fixed, and no uncertainty in model parameters. For the shale gas model must be considered that the composition variations affect natural gas production, due to shale gas composition changes within development areas. Then the variable composition shale gas development problem must be modeled. The modeling challenges are: composition variations affect well profitability, and producers must satisfy gas quality specifications at delivery nodes. Below, a realistic case of shale gas production network optimization is presented. The problem scope: greenfield development 10-year planning horizon, 10 candidate well pads, 1 processing plant, 1 compressor station, 1 freshwater source. Composition variation is presented in 3 clusters, based on the distribution of the following gases: methane, NLG, and inert gases. A well pad is a location which houses the wellheads, for several horizontally drilled wells. The benefit of a drilling pad is that operators can drill multiple wells, in a shorter time, than they might with just 1 well per site. The results of the optimization process are presented in the image. The solid lines indicate the gathering network selected by the optimization model. The numbers over the lines indicate the selected optimal diameter, in inches. Processing plant capacity is 50 million standard cubic feet per day. The compressor capacity is 947 horsepower. The optimal drilling strategy is presented in the Gantt chart. Activity schedules are given by well pad, 9 in total, as the possible pad P2 is not used. In the red boxes, they present the number of wells drilled in each pad, when it is decided to increase production in the pad. The optimal development schedule is characterized by a large number of return to pad operations that maximize the overall equipment utilization. Topic: optimal planning of oil well platform operations. In this case, the field infrastructure can be composed of a floating production storage and offloading, FPSO, or a tension leg platform, TLP, facilities. The FPSO facility can be either a small FPSO, converted from a retiring oil tanker, or a large FPSO, a newly constructed grassroots facility. An FPSO facility can process, store, and offload the processed oil to other tankers. Processing means separating the oil and water that comes out of the well. Unlike FPSO, a TLP facility cannot process oil, it possesses only drilling and oil recovering capability. TLP and FPSO facilities can be connected to each other through pipes, called risers. Oil recovered from TLP facilities is pumped to FPSO facilities through these pipes. Each facility has a construction cost, and a lead time between the construction decision and the actual startup. There are two options for drilling wells. Each well can be drilled either as a subsea or a TLP well. Drilling ships are used to drill subsea wells, so there is no need to have a facility present to drill a subsea well. Unlike subsea wells, a TLP well must be drilled by a TLP facility. Due to economic reasons, each type of well is drilled in groups consisting of fixed number of wells. In order to recover oil from a well, it must be connected to a facility. A subsea well must be connected to an FPSO facility, whereas a TLP well must be connected to a TLP facility. The uncertainties associated with optimization models are initial productivity per well, size of the reservoirs, and water breakthrough time for reservoirs. The main decisions are number and capacity of TLP and FPSO facilities, installation schedule for facilities, number of subsea or TLP wells to drill, and oil production profile over time. The optimization model for the planning of offshore oil and/or gas field infrastructure optimizes investment decisions, maximizing the expected net present value. The interaction between decisions creates many trade-offs and makes the decision-making process highly complex. There are four major assumptions in the problem about the state of the reservoir. First, there is no free gas in the reservoir. Second, there is a strong aqueous support which creates enough pressure in the reservoir. Third, there is no need for enhanced recovery, no injection of gas or water into the reservoir. Finally, all wells in one reservoir are identical, which leads to the same maximum oil flow rate for all wells in the reservoir given the cumulative oil extracted from that reservoir. These assumptions are made for the sake of simplicity, and both model and solution algorithm are flexible enough to incorporate more complex reservoir models. Three types of variables are used to represent decisions in mathematical modeling. Continuous variables, related with, materials flows, and financial flows. In each site, each period, and each scenario. Binary variables, related with, topology and logic variables in each period and each scenario. Integer variables, related with, the number of facilities available in each site, each period, and each scenario. Graphical representation of the aggregate infrastructure. The diagram shows the interconnection of production variables in multiple reservoirs using multiple type of facilities. Uncertain parameters in the system are initial maximum oil flow rate, recoverable oil volume and water breakthrough time of the reservoir. Considering that all wells in one reservoir are identical, it is considered the uncertainty in initial maximum oil flow rate for only a single well in the reservoir. The three uncertain parameters affect the nonlinear reservoir behavior in different ways. The nonlinear reservoir model is based on three equations that represent the dynamic behavior of the reservoir, in terminus of the proportions of oil and water that can be extracted. Equation 1. The nonlinear reservoir model shows oil and water flow rate from a single well versus the cumulative recovered oil. The maximum oil flow rate can be represented by a nonlinear function of cumulative recovered oil from the reservoir. Equation 2. During oil recovery from a reservoir, the liquid coming from the well contains not only oil and gas but also water, and the relative rates of these liquids can be characterized by the water-to-oil ratio. This ratio is approximated using a nonlinear function of the cumulative oil recovered, and the recoverable oil volume of the reservoir. Equation 3. The water rate can then be calculated by multiplying the oil flow rate by the water-to-oil ratio. These equations must be adjusted for the case of shale gas. Below are the results of the model. The presentation is aimed at understanding the implementation and the results obtained with a stochastic programming model. The tree of random scenarios covers a period of 4 years. The first 3 associated with an expansion or investment decision stage. In the first stage, it is considered that 5 random events may occur. In the second stage, random events do not occur. In the third stage, events occur in 4 of the branches of the scenario. In the middle branch, it is assumed that the same condition is maintained. In each branch with random events, it is assumed that 2 events may occur related with the breakthrough parameter, BP. The scenarios are high BP and low BP. The decision of the here and now, that is the one that must be implemented during the first period, or fifth stage, is to build 12 small FPSOs and drill 12 subsea wells. At the beginning of the second stage, it is considered that 5 random events may occur, characterized by the reservoir size, RS, and the initial productivity, IP. Decisions at this stage are mainly the function of the RS and at the secondary level of the IP. If things go very bad, only 12 subsea wells will be built. But, if they go very well, 5 small FPSOs and 3 TLPs will be built. The optimization model proposes solutions proportional to the bonanza that brings the decisions to develop the oil fields, conditioned in the random events that may occur. In the third stage, third year, it is considered that no random events occur, and that the situation of the project remains the same. The optimization model proposes solutions proportional to the bonanza of the project, which depend fundamentally on the condition of the IP parameters. As you can see, as IP decreases, more wells are drilled. This, presumably, to recover the initial investment, keeping the same amount of oil extracted. In the fourth stage, random events are considered, but not investment decisions. It is included in the model to refine the estimate of future costs. In long-term mathematical models, in order not to explode the number of periods, in many cases, it is customary to assume that the last period will be a stationary period, that will be maintained throughout the useful life of the project. This involves projecting and summarizing the future operation, in the last stage of the model. Economically, the model must be characterized probabilistically. In this case, the expected value of the net present value, NPV, is $4.92 billion for the 10 years of the planning horizon. Computationally, the differences between alternative methodologies to solve the mathematical problem may be very significant. In this case, a simple integrated algorithm would take 120 hours to solve what a high-level algorithm, based on partitioning and decomposition methodologies, would solve in 5.2 hours. The speed-off of advanced mathematics implies a ratio of 23.08 to 1 time faster. The non-anticipative variables and constraints are those that facilitate the construction of the tree of events and decisions. To understand this process, it is suggested to the interested listener to review the lectures on the theory of stochastic optimization modeling. The image presents the proposed structure of non-anticipative variables. Topic: EQT, Real-World Case Study. It is presented detailed in another conference. This real-world case study is related with the planning of shale gas exploitation for oil express. The fundamental problem is the design of the shale gas exploitation network, considering 2 types of transport modes, trucks, and pipelines. The statement of the problem is: given water sources, historical river flow rate data, well pads available, date restrictions, drilling completion date, piping connection date, lease termination date, and frac crews available. Determine well pad fracturing start date, hash of frac trips per day for each well pad, and starting date of fracturing holiday. Objective: determine the fracturing schedule that minimizes water transportation cost, trucks plus pipeline. Assumptions: can only pump from the impoundment at the max rate or zero, and aggregated well pads operations. The image shows the dimension of the problem. The image shows the drilling strategy by areas. Proposed solution algorithm for the shale gas development problem. Comparing the heuristic solution, based on good practices, with the stochastic optimization model, a fundamental change of strategy is obtained, which substantially reduces the operation with trucks. The cost of transportation is reduced by an order of magnitude, due to 14,010 truck trips are reduced to 1,350. CO2 emissions from trucking reduced from 630 to 60 metric tons. This implies a cost reduction of the order of 18.2%. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.